So this is Physics Lab 4 Oscillations. My name is Alexander Nguyen. Um, so the goal of this experiment was to analyze how a spring mass system behaves when the mass not only oscillates up and down but also swings in an arc. So to do this, I captured the motion using tracker, recorded the object's position over time, and then modeled the same system computationally in GlowScript using Newton's second law and the spring force equation. By comparing both results, I was able to evaluate how accurately the model predicts real motion and determine whether total energy is conserved throughout the oscillation. Okay. So in this experimental portion, I analyzed the two-dimensional motion of the spring mass system. Once the mass was released, it experienced only two forces, gravity pulling it downward and the restoring of the force of the spring. I used a meter stick in the background as a calibration reference to convert pixel distances into real-world lengths. And then afterward, importing the video into Tracker, I tracked the motion frame by frame and plotted the x and y displacements versus time. These plots allowed me to determine the period of oscillation and later compare those values directly with the simulation. Alright, now the GlowScript model. I recreated the same system computationally in GlowScript. The model included the spring and attached mass with gravity acting as the external force. I assumed the mass started from rest at the moment of release and imported its initial position from the tracker data. I simulated the simulation, then calculated the object's motion over 109 data points. So I could overlay it with observed data and see how closely it matched. This helped visualize how theory and experiment could align. We could compare afterwards. So code initial conditions. For the computational model, the mass spring constant and equilibrium length were predefined. I use a very small time step change of t to ensure the force updates at every iteration. And then the fundamental equations implemented were kinetic energy, spring potential energy, gravitational potential, and then these relationships let the program continuously update position and velocity, maintaining precision while showing how energy transfers between kinetic, gravitational, and elastic forms. Okay. And here is my results of the data. You can just compare each one and see how it lines up. Now, when comparing the experimental and simulated results, I found that the trajectories in both x and y directions nearly overlapped. Pretty much, their oscillation periods were consistent, confirming that the model captured the main dynamics of the system. However, in the y direction, the data showed slightly more variation, probably due to a resistance or something, which a lot didn't include. Energy graphs from the simulation also oscillated. Kinetic potential energies continuously shaded magnitude, while total energy remained constant, pretty much, supporting energy conservation. Yeah, so that's what that means. So additional questions. So from the energy plots, it's clear that energy principle is satisfied as kinetic and potential energies oscillate out of phase, demonstrating that energy shifts between those forms without loss. The total energy line stays constant, meaning the system conserves energy throughout the motion. Using tracker data, I calculated the oscillation period in both directions, 0.8 for x direction, 0.8 for the y direction. Both values are identical. We can conclude that x and y motions are synchronized, and the coupling between the spring force and gravity causes the mass to move smoothly in an elliptical path, maintaining a consistent period in both axes. This agreement between, and that's what that kind of means, right? It shows that you can simulate your data and model accurately with the real world oscillations and stuff. And that's it. Thanks.